Hello my dear students, this is Akash HD. Welcome to the ASD Physics classes. Hope so you all are doing really great. So students, in this video we are going to solve the MCQ, AR and case based questions. Okay, we have observed that this year most of the MCQ question came from dual nature of radiation and matter. If I talk about AR questions, all 4 AR questions came from NCERT Part 2, like from the chapter Ray Optics, dual nature of radiation and matter, nuclei and semiconductor. After that, at last, if I talk about the case-based question, that question came from the semiconductor, conceptual question, that much numerical and all was not required. Okay, so let's learn all these things in this video. Here, so you can see here, the first question is from the wave optics here. So see here, two coherent waves, each of intensity I naught, produce interference pattern on a screen. The average intensity of light on the screen is how much here? Okay, so this question is based from the chapter wave optics here. So here, if I talk about here the given data, so both the waves are having the same intensity, how much here? I naught, is it? After that, they are asking the average intensity. So remember that here, to calculate the average intensity, the formula is there, maximum intensity plus minimum intensity by 2. Maximum intensity will be there when the phase difference between the two waves is a 0. That means they are in a same phase. Minimum intensity will be there when both the waves are in out of phase. That means phase difference will be 180 degree. Okay. To solve this question, remember that here we need the intensity formula. What is the intensity formula? If I talk about here, resultant intensity formula is I1 plus I2 plus 2 root I1 I2 cos phi. Okay, if the intensities are different, you can use this formula. But if I talk about when the intensity is same, like I1 is I naught, I2 is I naught, so when you will simplify this, the formula used to come 4 I naught cos square phi by 2, is it? Where I naught is the individual intensities. Okay, so from here, if I talk about here the maximum intensity, which intensity? Maximum intensity. This phase difference phi will be how much here? 0. Okay, and you know very well cos 0 is 1 only. So I can write here, see, 4 I naught, and here you put cos square 0 by 2, cos square 0, cos 0 is 1, 1 square is also 1. So 4 I naught into 1, maximum intensity will be 4 I naught, is it? After that, if I talk about the minimum intensity, so for minimum intensity, remember that here 4 I naught cos square, this phi will be how much here? 180 degree, okay, or we can tell pi radian, anything is okay. So 180 by 2, how much is coming here? 90, cos square 90, and you know cos 90 is the 0, is it? So here what will come here? Here 0 will come here. If I talk about in case of YDSC, if both the waves are having the same intensity, what will be there? The dark fringe will be completely dark. Why? Because here minimum intensity is coming 0. For that, amplitude or intensity should be same. I am telling the some more basic. After that, if I talk about here the average intensity, as I have told the formula, I max plus I minimum by 2. So I max is 4 I naught, is it? I minimum is 0 by 2, so it will come here 2 I naught, is it? So 2 I naught, you can see which option is correct here. The correct option is here, option C is the answer, is it? Option C is the answer. Now students, after that we will move for the next question from the dual nature of radiation and matter. See here, the work function of a material is 2.21 electron volt. Which of the following cannot produce photoelectron from it? Okay, so here if I talk about here, first they are talking about the work function. Okay, so work function is given by, work function means minimum energy required to take out the electron from the metal surface. So phi naught is given here, see here, 2.21 electron volt, that is the work function. And one more thing, remember that here, with this I will tell you, to take out the electron from the metal surface, frequency should be more than the threshold frequency, okay, and wavelength should be less than the threshold wavelength. This also we should know that here, okay, and this condition are satisfied because in the question they did not mention, that means by default this is there, okay. Whenever the electron will come out from the metal surface, in that situation only, when the electron has to come out from the metal surface, okay. After that, remember that here there is the Einstein photoelectric equation. What is the Einstein photoelectric equation? It is that K max is equal to E minus phi naught. Why K max? Because electron is coming from the metal surface, then only K max. E is the incident energy and phi naught is the, as in the question they told, work function. Okay. So remember that here, electron will only come out from the metal surface when this K max will be greater than 0. When K max greater than 0, then only we can tell electron is coming out. That means we can tell E minus phi naught should be greater than 0, then only electron will come out. Okay, or hence we can tell here, to take out the electron from metal surface, incident energy of the photon should be more than the threshold, not threshold, actually what is given, work function, is it? Now after that here if we talk about here, to calculate the energy, they did not given anything, they only talked about the light and all, and in this MCQ question only one is correct. Okay, so here we have to see the energy. Energy is given here, you know, h nu, is it? Energy h nu, and nu means hc by lambda, is it? So from here we can tell here energy is inversely proportional to lambda, is it? After that we know that here if we talk about the VIBGYOR, now you know VIBGYOR, na, VIBGYOR. So in VIBGYOR, which light is having the maximum wavelength? Red. Which light is having the minimum wavelength? Violet, is it? So if I talk about here, see, lambda R is maximum, red light, na. After that VIBGYOR, VIBG, then after that lambda green is there, is it? Then after that VIBGYOR, VI, see, VIBGYOR, okay. So red is there, after that green is there, then after that they are telling blue, is it? Lambda blue, then after that what will come? Lambda violet will come, is it? So from here, now you know energy is inversely proportional to wavelength. That means if I tell that here, red light is having the minimum energy, then green, then blue, then violet. That means the most probable chance is there, which one is having the minimum energy? Red light is having the minimum energy, is it? And you know very well the energy should be more than the work function, is it? So as ER is a minimum, ER is minimum, that means the most probability is there, the red light, by using the red light we cannot take out the electron from the metal surface. After that with green, more possibility is there, blue, more and more possibility, and violet, maximum possibility is there. Na? But here they are telling that here which one option is correct, which cannot take out electron from the metal surface. So where energy is minimum for the red light. Here minimum chances are there, or what we can tell, maximum chances are there, so that electron will not come out from the metal surface. Again I am telling which chance? Maximum chance. Why? Because energy is a minimum, is it? So we can tell very well the red light cannot take out the electron from the metal surface because its energy is minimum. Why? Because lambda for these lights are some ranges are there, and in the exam we cannot remember wavelength of all the lights and all that. Okay, so in a very logical manner we have to go and we have to just solve this question. Okay, so answer is the red light, because energy is minimum, maximum chance is there, red light will not take out the electron from the metal surface. Okay, great. Now let's see the question is, the momentum in kilogram meter per second of a photon of frequency 6 into 10 power 14 hertz is how much here? Okay, so here we need the momentum. So you know very well, remember that here which word is there? Photon. Okay, and photon travels with the speed of light. Have to be very careful whenever they are telling about the photon travels with the speed of light. Okay, and after that let's take some other particle, electron, proton and all that. Here they will travel faster, but most of the time, or mostly all the time, they will not travel with the speed of light. So whenever photon, you have to think about speed of light. Whenever electron, proton and all is here, that time you have to think from the dual nature of radiation and matter. There de-Broglie hypothesis is there. Okay, so photon means speed of light only. So for photon we can write here E equal to mc square, and I have told you h nu also, is it? After that if I take this, so from here we can write here m into c, and one more c will be there, that will go this side, is it? And what is mc? You know very well, momentum means mass into velocity, is it? They are asking momentum. So we can write P equal to h nu by c. This formula is there to get the electron. What to tell? Here momentum how much here? H nu by c, is it, for the photon? Okay. So if I talk about here, this P is given by here. What is the value of H? We know very well. 6.6 into 10 to the power minus 34. Unit will be joule second, but anyhow everything in SI, no need to worry about the unit. After that, frequency, they are telling how much here. Frequency is this one here, 6 into 10 to the power 14. Whenever traveling with the speed of light, we will use for frequency nu. We will not use F and all. Okay, speed of light means nu. What is given here? 6 into 10 to the power 14 by, see how much we know, 3 into 10 to the power 8. Is it? Then after that, what will happen that here? All the numbers we will collect together, 6.6, 6 and 3. Even we can tell 3 to just 6. Is it? So we can write here 6.6 into 2 into. If we just simplify the power and all that, so what will happen that 8 will go up. So 14 minus 8, that means it will become 6, 10 power minus 34. See, 10 power minus 34 into this 8 will go up. 14 minus 8 means 6. And here what will happen that here, see, 2 6 is 12. 1 will go this side. 13.2 into 10 to the power minus 28. Correct? So here, see here, the powers minus 28 is not there, but see here, this is matching somewhat. So 1.32 into 10 to the power minus 27 kilogram meter per second. Is it? So 1.32, which option is nearly matching? Option B is there. And again I am telling, remember that photon will travel with the speed of light. You can use equal to mc square equal to h nu. Is it? Great. Now students, next one, what is the question? See here. The wavelength of a photon, see, the wavelength of a photon is equal to the wavelength associated with an electron. Both will have the same value of. What they are telling? The wavelength is same. Okay. So again, de-Broglie hypothesis is there. Wavelength formula is given by lambda equal to h by p. Now this is the wavelength. Lambda is the wavelength, h is the Planck's constant, p is the momentum. Which momentum? Linear momentum. Okay. After that, what they are telling that? They are telling that here lambda of photon is equal to lambda of electron. When it is possible, because you know anyhow h is constant only. No? So when lambda is equal, that means the most probably, definitely the momentum of photon will be equal to the momentum of electron. Momentum of photon will be equal to the momentum of electron. Which momentum? Linear momentum. So where it is there? The correct option is here. Option D is the answer. Okay. Even if we talk about here the, see here, the momentum. So momentum means you can see here mass of photon into speed of photon means speed of light. Is it? And here means mass of electron, and we can tell speed of electron. Is it? And as I have told you, photon travels with the speed of light, and electron, it will not travel with the speed of light. Is it? So we know very well here, their speed of electron is anyhow less than the speed of light. So as the speed of electron is less, so to make both of them equal, what will be there? The mass of the electron is more than the mass of photon. Okay. Anyhow, answer came linear momentum, but I have told you very basic. Is it? So speed of electron is less than the speed of light. Product mass into V is constant both the sides. So definitely mass of electron is more than the mass of photon. Which mass of the photon? When the photon is moving. Two kinds of mass is there for the photon. Rest mass of the photon is 0. But kinetic mass of the photon, you know, equal to mc square. So from there we can get m equal to E by c square. That is called the kinetic mass of the photon. Okay. Rest mass of photon and kinetic mass of photon is different. Is it? So option D is the answer. Now students, after that, next question. What is the question? See here. Again, dual nature of radiation and matter. See. The de-Broglie wavelength associated, even they told name even, de-Broglie wavelength, with an electron moving with energy 5 electron voltage, how much? So de-Broglie hypothesis tells that like a light is there, na? Light is a wave or particle. Light can behave as a, see, normally we used to know that light is a wave. It behaves as a particle also in a Einstein photoelectric equation. Similarly, if any other particles are there like electron, proton, they are particles, but sometimes they will behave as a wave also. To calculate their wavelength, there is the de-Broglie wavelength is there. Okay. So what is this here? You can see very well, students. The energy of the photon is given. No? K, will write here K. It is given a 5 electron volt. So we can write here 5 into 1.6 into 10 to the power minus 19 joule. I am solving everything in a SI unit. Okay. After that, no other data is given. So de Broglie wavelength is given here, lambda equal to h by p. P is the momentum. And you know, in 11th we have learned relation between kinetic energy and momentum. So momentum is given by even root 2 mk. Which particle is there? Electron is there. No? So I will use me. No? So to calculate the wavelength, we have to put. Now calculation is started. H how much here? See, 6.6 into 10 to the power minus 34. Is it? After that, see here. Big calculation is there. 2 mass of electron how much here? 9.31 into 10 to the power minus 31. Is it? That is the mass of the electron. Kinetic energy how much is given here? Kindly see here. 5 into 1.6 into 10 to the power minus 19. Is it? This is the mass of electron and this is energy. Okay. Now after that here, again we will simplify this here. Say 6.6 into 10 to the power minus 34. Is it? Now we will collect all the numbers first together. All the numbers I have collected. Now, so what will happen that you see? 2 into 9.31 into 5 into 1.6 into. If you see that 10 to the power how much here? Here minus 31 and here how much here? Minus 31 and minus 19. 31 and 19 what will be there? So 31 plus 9 40 and 10 to the power minus 50. Square root of 10 to the power minus 50 means outside it will come 10 to the power minus 25. Is it? After that, see this side I will just do the calculation. No, see here I am doing the calculation. So here what will happen that here, see this lambda is given now 6.6 into 10 to the power minus 35. Calculation is there only. Now here what will happen that here, see 5 into 1.6 1.6 into 5 it will come 8. 8 into 2, 16 and this 9.31 approximately I have taken 9. So 1.6 into 5, 8. 8 into 2, 16. 16 into 9, 144 approximately. 144 into 10 to the power minus 25. Is it? So we can write here say 6.6 by 12 and here it will come here into minus 25 will go up. So it will become plus 25. That means 10 to the power minus 9. When you will simplify this 6.6 by 12, it will come approximately. Now I have done the approximation 9.31. I have taken 9. So it will come here nearly 0.55 into 10 to the power minus 9 meter. 10 to the power minus 9 meter means nanometer. Is it? So we can write here 0.55 nanometer. Why we have done approximation? Because all the options are far, not too much very closer. So what is the answer? 0.55 nanometer. We have used the de Broglie hypothesis. All this calculation is there. If you know some other way also to shorten the calculation, you can do it. But anyhow, option is there, option D, 0.55 nanometer. Okay, great. Now students, after that, next one from the nuclei. After solving so many questions of dual nature of radiation matter, now nuclei is there. So see here, inside a nucleus, the nuclear forces between proton and proton, proton and neutron, neutron and neutron are FPP, Fpn, Fnn respectively. Then these 4 options are there. Okay, so whenever we will read the nuclei chapter, we read the properties of the nuclear forces, and one of the very important properties that what is a very important property? Property is that nuclear forces are charge independent. What is the property? The nuclear forces are charge independent. So as nuclear forces are charge independent, now whether positive charge, negative charge, neutral, all these things does not matter. That means what we can tell, force between whether it is the proton-proton or it is between proton-neutron or it is between neutron-neutron. What will be there? All these forces will be same. Na? Short range force. Nuclear force is a short range force. Okay. So which option is correct here? Option D. This question was very easy. Na? Within seconds we can answer. Is it? Great. Next one now, after completing all these 6 MCQs, now we are going to solve 4 ARs. And as I have told you, all AR came from NCERT Part 2. Okay, so let's see here. Here assertion region is there and here these 4 possibilities are there. But make sure that here, what they're telling that here, both A, assertion may be true, assertion may be true, assertion may be true. So see here, if assertion any time is true, there is the 3 possibilities are there. But if in case assertion went false, then answer will become very easy because these three options will cancel out and directly we can go for option D. So if the assertion went false, very easy, this question will become very easy. But if assertion is true, then we have to see region also very well, is it? So see here, the question is what assertion? In a reflecting telescope, see the term reflecting, reflection in a mirrors, refraction in a lenses. So reflecting telescope, that means here we will use the mirrors. No? So in a reflecting telescope, the image does not have chromatic aberration. Okay, this is the assertion. So I am telling you here, in a reflecting telescope, we use only and only mirrors, and chromatic aberration happens when the different colors of light could not focus at the same point and they will not make the point image. Okay, so in a reflection type of telescope, this chromatic aberration is not at all possible. Chromatic aberration is only possible in a lenses, not in a mirrors. That means anyhow they are telling that image does not have chromatic aberration. This is definitely correct, definitely correct. Okay, now after that, see the region. Chromatic aberration occurs only due to refraction of light through an optical medium. Yes, that also I have told you. And remember that here, students, here what I have told you, chromatic aberration is see here, chromatic aberration in mirrors. Chromatic aberration in mirrors does not happen. No, does not happen. This only happens where? This happens only in a lenses. Why it happens? This happens that because wavelength of colors of light is different. Like I have told you very well, like lambda r is greater than lambda v, is it? And you know one more formula is there. I will write here, see, 1 by f equal to formula is there, see, 1 by f mu minus 1, this is the formula, 1 by r1 minus 1 by r2, is it? Or we can tell 1 by f is directly proportional to mu. What is mu? C by lambda. So we can tell here f is directly proportional to lambda, is it? See here f, here lambda. So what will happen? Lambda r is greater than lambda v, so we can tell here Fr is also greater than Fv, is it? That means focal length for different colors of light will be different because of this nature only. What will happen that the different colors of light will focus different and image will not be point, it will be somewhat blurred. And this will happen where? This will happen in lenses. This chromatic aberration will happen where? This will happen in lenses. This will not happen in a mirror. This will happen in lenses. Okay. So remember that here this option is also correct only. Okay. But here they are talking about the reflection. Here they are talking about the refraction. And as I have told you, chromatic aberration does not happen in a reflection, only happens in a refraction. There is no relation of chromatic aberration to the reflection. Okay, reflection is independent of chromatic aberration. So here both are correct, but region is not explaining the assertion correct. Okay, so which option is correct here? The correct option is here option B. I have told you chromatic aberration is independent of the reflection. That's why both are correct, but region is not explaining the assertion. Okay, great. Next one, let's see here, students. X-rays. Normally we used to think that X-rays are not in a CBSE syllabus because it used to come in a J exam, but board exam means all time they are putting different kind of scenarios they are putting. So it is teaching us nothing should be left for the board exam if we want to get centum in a exam, is it? Everything we have to study, whatever is there in a syllabus, even in a NEET syllabus also, J syllabus also, because we have to prepare our best. Okay, so see here now X-rays they have asked. I told you, this is the part of the J syllabus, but they are asking here, so we have to prepare all the things. So see here, X-rays are produced when slow-moving electrons are stopped by a metal target of a high atomic number. No, this assertion is wrong. Why this assertion is wrong? That means the electrons should not be slow. The fast-moving electrons will strike the heavy metal target. So when the fast-moving electron will strike the heavy metal target, suddenly their kinetic energy will decrease. So when the kinetic energy will decrease, that kinetic energy will release in the form of X-rays. Okay, so see, assertion is wrong. So assertion is wrong. Anyhow, ABC is not possible. Option is D only. So assertion is false. Region is also false here. So see here, X-rays consists of low energy photons. That is also wrong. Not low energy photons. It will have the fast energy photons. And here also not slow. This is also fast. So the anyhow, assertion is also wrong, region is also wrong. The correct option is here, option D is the answer. Is it? Which option? Option D is the answer. Now, Next one, let's see here, students. The question is from the nuclei. The binding energy per nucleon is partially constant for mass number in the range 30 to 170. Okay, so here one thing, students, remember that here, just what will happen that here you should know energy, binding energy per nucleon versus mass number curve. Okay, so if in case when you know binding energy per nucleon versus mass number curve, I will just draw here. The curve looks like this, is it? The curve looks like this here. Now, this side mass number, this side binding energy per nucleon in a mega electron volt. Okay, so what will happen that here when we used to draw the curve like this here, now some spikes will be there and then it used to go like this, is it? So here what will happen that here, students, here normally the see little bit mistake happen. Why? Because see like this. Okay, now okay, now what will happen that here, students, in this if we talk about the top point, at the top point iron used to be there. Okay, and from nearly what we can tell 50 to 80 the curve is having the flat maximum. Where to where? 50 to 80 curve is having the flat maximum. But if we talk about here nearly 30, and here also we can talk about here what they're telling 170. So I am telling 50 to 80 flat maximum is there, maximum, but 30 to 170 also what is there, 30 to 170 also practically we can tell here. See, when I am drawing here now it is looking more curved, but when we will see that practically that much curve will not be possible. Practically we can tell okay somewhat little bit constant and all that here. Okay, so remember that here, and here these spikes represents the magic number. We can tell helium, carbon, oxygen. This used to be the helium, carbon, oxygen and all that here. Okay, so remember that here. Again I am telling okay 50 to 80 is the flat maximum is there, but 30 to 170 also practically constant. Practically. No? So see here, they are telling here the what? Practically constant. Okay, so this one is correct only. Even in your book also you open the nuclei chapter and you see here, you will see that 30 to 170 it will be practically constant, roughly constant. Okay, so see here, region, the nuclear forces between the nucleons for mass number in the range 30 to 170 are not short range. See here, are not short range. As I have told you what, the nuclear forces are short range only, but here what they are telling, not short range. Okay, that means anyhow this region is wrong. So what is given here, students, if you will talk about all the possibilities are A is true but R is false. The correct option is here, option C is the answer. Is it? Great. Next one, let's hear, students, this question from the semiconductors. See very well, see, a hole is an apparent, see apparent means imaginary, na? A hole is an apparent free particle with effective positive electronic charge. Is it? Why? Because what happens that here, when in a semiconductor two kinds of carriers are there. One is the electron, one is the hole. So electron is the okay actual particle, but what is this? The hole is what? The hole is the apparent particle. Even if we talk about here the bands also, let's take for example I am talking about here the energy band. Normally I have taken intrinsic semiconductor at T greater than 0 Kelvin. Is it? So what used to be there? This is the conduction band and this is what? This is the valence band. Between them energy gap is there. So what will happen that here, students, at room temperature some of the electrons may jump from valence band to the conduction band. Is it? So here, so when the electron will jump from valence band to the conduction band, here what will be there? Here I am talking about the intrinsic semiconductor at room temperature, T greater than 0 Kelvin, even T greater than 300 Kelvin, okay, room temperature. So when the electron will jump from valence band to the conduction band, electron will go, but here how many electrons went? 1, 2, 3, 4, 5. So here what will happen? Holes will also create here, okay, 1, 2, 3, 4, 5, 6, is it? So see here, electron is actual particle, but what I am coming to tell you with this, electron is actual particle, but hole is what? Apparent particle. Hole will create when electron will leave their space. Is it? So what they are telling that here, hole is an apparent free particle. Apparent. Why? Because electron has left their place and it has become hole. Okay. So anyhow, this is correct only. Electron anyhow negative, holes will consider positive. Correct only. After that, see, a hole is not necessarily a vacancy left behind by an electron in the valence band. Not necessarily, but remember that here it's not about the not necessarily. it is necessarily, not necessarily when the electron will jump from valence band to the conduction band, then only hole will create. The definitely what should be there, students? Vacancy should be left. So not necessarily, this not word only is making this region is wrong. Is it? So assertion is right, region is wrong. Necessarily there is the vacancy left in a valence band when the electron is jumping from valence band to the conduction band. I am telling the intrinsic semiconductor. Still, I did not take any doping and all that. Okay. So which option is correct here? A is true, R is false. The correct option is here. Option C is the answer. Is it? Great. Next one, students, we came to the case-based questions, and here this is from the semiconductor electronics. You know, in a case-based questions, they will give some information also. Okay. Sometimes information is useful to solve the question. Sometimes not useful. Simply they will just okay put for filling the gap. Okay. So here you can see some information is there based upon case-based question. You can read it very peacefully, no problem. Now you can pause the video and you can read it here. Okay. But what I observed, this information was not that much useful. Okay. So see here also this is there. Now you can pause the video and you can read it here. Is it correct? Now we'll come to solve the questions here. Okay. So what is the question here? See the first question. Which of the following is a donor impurity atom from germanium? Is it? You know, two kinds of semiconductors are there. One is a silicon, one is germanium. When the silicon, okay, I will take the example just silicon. So when silicon in a pure form, there is no doping and also that is called intrinsic semiconductor, but their conductivity is the very less. To make them somewhat more conducting, what we'll do the doping. So what will happen that here? When this doping is done by some pentavalent. Which one? Pentavalent impurity. Now then this will become which one here? This will become here N-type semiconductor. Is it? And that is called which impurity? Donor impurity. And this pentavalent impurity is used to be phosphorus, arsenic, antimony. When we are doping with phosphorus, arsenic or antimony, pentavalent impurity means in their outermost shell 5 electrons are there. Okay. So they are asking a donor impurity. Now which option is correct here? The correct option is here antimony. Antimony is the donor. But just for the information purpose, when we are doing with the trivalent impurity, it will become P-type semiconductor. And what are the their even name is there. See, boron, aluminum, indium. This boron, if we'll talk about here, boron, aluminum, even in indium, they all are which one? Which one? Acceptor. This is the donor impurity. This is the acceptor. Okay. So remember that here the correct option is here. Option B is the answer. Is it? Now see the second question. Looking somewhat big now. See here. When a pentavalent atom occupies the position pentavalent, see the N-type semiconductor, pentavalent of an atom in the crystal lattice of silicon, 4 of its electrons form covalent bonds with the 4 silicon neighbors. Now covalent bond will form. This impurity atom will make covalent bond with the neighbor silicon atoms, while the 5th remains bound to the parent atom. Okay. The energy required to set this electron free is about, and here 4 options are there. Here calculation and all we cannot do it because that much information is not available. For that we should go to the extrinsic semiconductor. Which semiconductor is there? Extrinsic semiconductor. So see here I have taken the extrinsic semiconductor. Now normally what will happen that here whenever we will add the impurity, let's take N-type means what we are adding? We are adding maybe phosphorus, arsenic or antimony. So when we will add this, you know what will happen that here one donor energy level will create near to the which band? Near to the conduction band. This is conduction band, this is valence band. Okay. So the moment we'll do the doping, one donor energy level will create here. Is it? And what is this? This is the EC, lowest energy level of the conduction band. Okay. So the difference between this EC and this ED for N-type semiconductor, it used to be the 0.01 electron volt given in the NCERT. Based upon that only I am telling 0.01 electron volt. That means here if electrons are there, donor atoms are there, they will donate the electron to the conduction band. When how much energy is required? It has to jump from ED to the EC at least. How much is given in the book? 0.01 electron volt here. Is it? And if we talk about here p-type, see in the question they ask n-type, is it? So in the book they have given 0.01 electron volt, so definitely I will go with the 0.01 electron volt. It is given in a book for the n-type semiconductor, 0.01 electron volt here. Similarly, for extra information, if in case p-type semiconductor is there, now I have told you boron, aluminum, indium, even one more is there, gallium is there. What is the name? Gallium. This 4 can produce p-type semiconductor doping. So here what will happen at here, when we'll dope with the this one here, so here one energy will create here. This is called the acceptor energy level. What will create the acceptor energy level? And here this is the lowest, this is the highest energy level of the valence band. This is the lowest energy level of the conduction band. This is the highest energy level of the valence band. So what will happen here? This is the valence band, this is conduction band, and here holes will create when? Holes will create when the electrons, what will happen? Electrons, these electrons are there now. These electrons can jump from valence band to this new energy level, and when they will jump here, what will create here? Holes will create. Instead of jumping to the conduction band, they will jump to the extra energy level here, is it? And here remember that here in NCERT they have given this level, that means EV to EC, now up to this is given here 0.01 to 0.05 electron volt. But in the question as they told n-type, so only I have taken 0.01 electron volt is there, is it? This is the basic. Little bit they have asked application based question. Okay, now students see next one. The question is what? See, during formation of a p-n junction. P-n junction means when p-type and n-type semiconductor is combined. So see here, options are there, a layer of negative charge on this, all these options are there. Okay, so see here I will just tell you basic here. So see here, students here, what will happen at here, let's take this is the p-type this side, this is the n-type this side, is it? In a n-type semiconductor, what will be there? Free majority carriers will be electrons, is it? And immobile positive fixed ions will be there. Okay, so what will happen that here some positive fixed ions are there. Positive fixed ions are there like this in a n-type, is it? And what will be there? Electrons will be there like this. Electrons will be there. Okay, and in the p-type what will be there? Negative acceptor ions will be there. Negative, and negative. Okay, negative. And here what are the majority carriers? Majority carriers will be holes. What will be there? Holes will be there. Is it? So when we are making this p-n junction, no, unbiased I am not taking any battery and all that. So you know what will happen that here, some of the electron will go from n-type to p-type and it will cause the diffusion current and all. Okay, but that is not required for this question. What will happen that here, remember that here I can tell you, see, this is positive is there, now this is positive, and this side what is there? Negative is there, is it? Negative is there. Okay, and here let's take here, I will just make here one layer like this. So what will happen that here, again I am telling you students here, from n side to p side, what will move? Electron will move, now because majority carriers are electrons. Electrons will move from n side to p side and it will combine with the holes. Okay, so when this electrons of n side combine with the holes, so here what will happen that hole and electron will combine and they will disappear, and what will happen? Only ions will be there. In a depletion region, only what is there? Ions. Which ions are there? Positive ion and a negative ion. Positive ion n side, negative ion n p side, is it? Is it? So remember that here what is moving? Electrons are moving, diffusion current. After that, to get the equilibrium and all that here, diffusion current will come. Then because of the minority carriers will move, that means from p side electrons and n side holes. So when they will move, drift current will be there. When both of them will become equal, then equilibrium and all will reach. Now that is all the story. Okay, but anyhow remember that here, based upon the question, if we see here, we can see this option B. See, a layer of positive charge on n side. See, on n side which layer is there? Positive side, because electron went. And a layer of negative charge on p side will appear. Others all are stories. Option B is the only correct one, is it? And here I have just discussed the unbiased one. Now battery is not connected. Next one, students, let's see here this question. What is the question here? In a reverse biased p-n junction, reverse biased, how the p-n junction will be reverse biased here? Here biasing is there. Okay, so what will happen that here, let's take here, this is p, this is n. Reverse bias means what will happen? The p will be connected to negative of the battery and n will be connected to positive of the battery. That is called the reverse bias. Okay, so here see here, in reverse bias, first option, the drift current is of the order of few milliampere. No, the drift current is used to be the order of the microampere. Okay, so anyhow this option A is wrong. Okay, next one, the applied voltage mostly drops across the depletion region. Okay. Third one, see, the depletion region with decreases. No, in a forward bias, the depletion region width will decrease, and in a reverse bias, depletion region width will increase. Okay, so here it should, instead of decrease, it should increase. Now, after, let's see, the current increases. D, the current increases with increase in a applied voltage. Here you remember that here, students, in a reverse bias, when you will increase the voltage, what will happen? The current will be independent of the voltage. That means voltage will increase, but the current will not at all increase. When current will suddenly increase, when the breakdown voltage will reach, then only current will suddenly increase. So till that time breakdown voltage is not reaching, even you are increasing the voltage also, current will not increase. It will be independent of the voltage. That is called the reverse current. Reverse current is independent of the voltage till the breakdown voltage is not reached. Okay, that means for this region only, D is also wrong. The correct option is there, option B. That means the applied voltage mostly drops across the depletion region here. Okay, and after that, this is the optional question is there now, because in case study 5 questions are there, we have to do any 4 now. So that is the optional question. See, what is the optional question? See, the output frequency of a full wave rectifier with 50 Hz as input frequency is. Okay, so remember that here, if I talk about here, 2 rectifiers are there, half wave rectifier and full wave rectifier. Okay, so see here, in a half wave rectifier, what will be there? The output frequency, or we can tell ripple frequency, is equal to the input frequency. That means 50 Hz. It is here. But if we talk about here the full wave rectifier, output frequency will be twice of the input frequency. That means 2 into 50, and it will come here 100 Hz. Remember that here. That means they are telling full wave rectifier. Which option is correct here? The correct option is here, option C. In full wave rectifier, output frequency, that means ripple output frequency is twice of the input frequency. Answer is 100 Hz. Okay, students. So I hope so in this video, 6 MCQ, 4 AR, and then this case-based 5 questions is very, very clear to you. Keep studying, keep going.